Okay, this is another video in the series for Math 1224 for UTSA. We're going to be dealing with Chapter 3, Techniques of Integration. So basically, as the title of the chapter is, Techniques of Integration, it's different ways to evaluate different integrals, different approaches. Substitution is an example of a technique that's covered in Cal 1. So we'll go through basically, here's the technique, here's what you do. And in some cases, we'll justify why the technique works, what's the basis for it. And also, we'll do some more application problems as we go along. As we get new integration techniques, there's new integrals we're able to solve, and therefore there's new volumes and surface areas and work and stuff like that we can calculate. So, first section is integration by parts. That's what this video will be on 3.1. The next video is on 3.2, of course. So, the differential of a product. So, if I have something like the differential of u times v, okay? And u and v are both functions of x. I don't want to write u of x and v of x every time because that just gets tedious, but they're functions of x. Well, there's a couple of ways to think about this. One way is to say that this is dx of the product u times v times dx. This would be just by definition of what a differential is from Cal 1. This is not the only way to do it, but this is maybe the most straightforward. So if I have the derivative of a product, well, I'm using the product rule, right? So this will be du dx, parentheses, times v plus u times dv dx, right? Times dx. Now, if I distribute the dx, this is du dx. It's not a t, it's just a badly drawn x, badly written x, times v times dx plus u times dv dx times dx. Okay? This is the order that I want the factors in, but this one, I don't like the order. I'm going to move the dx in between the du dx and the v. So this is du dx times dx times v plus u times dv dx times dx. So all of this is just algebra, right? I'm just distributing, reorganizing terms, commutativity. So if we examine this, du dx times dx, what is that, right? Now, if you take the naive approach, go, oh, well, that's a fraction. You just cancel. That's du. While technically incorrect, that's suggestive. This is why we use the fractional Leibniz notation, or that's why the fraction-looking notation even exists. This is why Leibniz chose it, because when you have a ratio of differentials, that's equivalent to the derivative, right? This is u prime, essentially. Okay, so this is du. Oops, let me change colors here. This is du times v, right? Plus u times dv. Okay, am I out of room? I'm almost out of room. So let's go start a new column over here, because we're not quite done with this. This is, we're building towards something. So I'm going to copy this over here. Okay, d of u times v equals du times v plus u times dv. Now what I'm going to do is I'm going to integrate on both sides. Okay. Now in this case, when you find the integral of a differential, you just get the variable, right? The integral of dx is just x. Well, plus c, but let's not worry about the plus c right now. Okay. So this left-hand side is just u times v. This equals, I'm going to switch the order here. Usually we put the differential at the end. You don't have to, but that's typically what we do. So v du plus the integral of u dv. And what I'm going to do is I want to get this by itself. And you'll see why soon enough. Like, why are we doing this? I'm just starting from the product rule to show that we're going to get a formula that we're then use to solve some integrals. So I'm going to subtract the integral of v du on both sides. So I get u times v minus the integral of v du equals the integral of u dv. And typically, this is written the other way around. This is the integral of u dv equals uv minus the integral of v du. This is called the formula for integration by parts. There are a number of integrals that require this technique, this formula essentially, where you're picking apart, oh, in my integrand, part of this is the function u, and the other part is the differential of some function v. And v is not explicitly present in your integrand, but its differential is present. And of course, we'll do examples. You'll see what I mean by that. So there we go. That's the formula we're going to use. But I just wanted to basically say that really what we're doing is this formula for integration by parts. This is the reverse of the product rule for derivatives. So essentially, when we would do integration by substitution, well, that's doing the chain rule backwards. When you do integration by parts, that's doing the product rule backwards. There's not really any analog for the quotient rule. That kind of gets swept up and dealt with by integration by parts. So really, integration by parts is the product rule and quotient rule together, reversing them. So, what does that look like? Oh, I accidentally reversed the product rule. So all of this was supposed to be down here. Oh well, that's fine. In fact, let's just do this. I guess I placed this ahead of time with correct spacing and then just forgot, oh yeah, I've left room. That's why I'm running out of room here. Anyway, we'll pretend that was that worked out nicely. Anyway, so reversing the product rule is what we're doing with integration by parts. So how do you apply this? So I have this integral, and basically there's no way to do a substitution that's going to solve this. You just kind of can't. Substitution simply does not work. In some cases, there are integral tables. You can Google integral table and find a big list of all these integral or antiderivative formulas. Obviously, we're not going to just do that. We're going to work this one out. So how do we do that? Well, what I'm going to do is this. In the integration by parts formula, the left-hand side is what we're starting with, and I have to identify u and dv. On the right-hand side, there's only one differential. It's u. So I want u to be something for which I know the derivative, or it's relatively simple. And I need v to be something for which, I need dv to be something for which I know the antiderivative, or it's relatively simple. So in this case, I'm going to say that this x, this is u, and sine x dx, this is dv. The differential with respect to x, the variable we typically start with, will always be paired with dv, or with the other component to make dv, rather. If I wanted to, this is optional, I could say, well, let me rewrite this and say, oh, well, this is sine of x times x dx. And I can call this u and call this dv. That's optional. If I want to, I can do that. In this case, that's not going to work. And in fact, I could even do this. I could say, well, let me rewrite this as 1 times x sine of x dx. Call this u and call this dv. Or if I want to, I can say, okay, let me rewrite this as x sine x times dx. Call this u and call this dv, right? There's lots of options, and the more factors that you have in your integrand, the more options there are. In most cases, in the video, I will just show you the one that's most straightforward or easiest, at least, to me. We may at times do more than one version to see what the different options are. I think typically there'll be one option that's easier than the other option or options. So I have u, so I'm going to need, in fact, let's just do this. So I'm going to need du. What's the differential of that? Well, if u equals x, then du. And in fact, you know what? Let's do it this way. I wasn't going to, but let's do this. Let's say u equals x and dv equals sine x dx. Okay, so that means that du equals dx. Just like if we were doing a substitution, we need the differential of u, right? And I should point out that you don't have to use U and V. You can use M and N, A and B, whatever letters you want. The letters don't matter. So now, try not to run out of room there. So now, I need to find V. V is the antiderivative of whatever the factor in dv is. So antiderivative of sine x, that's a negative cosine x. And of course, there was a plus c. However, we don't have to put the plus c. We could pick a number like plus 10 if you want, and that'll end up kind of not exactly canceling out, but it ends up not mattering. Maybe we'll. I think in the video I'm not going to bother doing that. But if you pick a number, you should check for yourself that you do get another viable antiderivative. I'll comment on that towards the end, but I'm not going to bother writing it out as we go along. But towards the end, I'll point it out. Hopefully, I remember. So that's equal to, well, I'm going to write out, uv minus integral v du. I'm going to write the formula every time so I don't forget it, right? So u, well, that's x. V, that's negative cosine x, minus the integral of v, which is negative cosine x, du, which is dx. So this equals negative x cosine x plus the integral of cosine x dx. And the point of integration by parts is that this integrand is a lot easier to deal with than the one we started with, right? There's no x there anymore. So the fact that I got to get rid of this because du is dx, so I just had the differential of the independent variable. That's the point. That's why this works. So now I can say, all right, so this equals negative x cosine x plus sine x plus c. Okay. So if I had chosen a number up here, like if I had done plus c or plus some whatever letter, or plus 10, pick a number, at the end, that plus 10 would end up kind of lumping in with the plus c. And it wouldn't serve a purpose anymore. It wouldn't need to be there, really. So you just don't need it, essentially. Let's check that this is correct. Because, I can say this, and you go, okay, fine. I mean, if you followed the rearrangement I was doing up here, then that's great. But how do we know this is correct? So anytime you have an antiderivative, really, by definition, an antiderivative is some function that when you find the derivative, you get the original. So let's find the derivative of this and confirm that we really do get x sine x, right? We should get, if we differentiate, x sine x, right? So let's check that. So dx of negative x cosine x plus sine x plus c, well, yeah, I'm running out of room here, equals. So I need to apply the product rule here, right? I have a product of two functions. So this will be dx of negative x times cosine x minus x times dx of cosine x. You try to squeeze a little more in there. Plus dx sine x plus 0, right? The derivative of c is 0, of course. It's going to bother me if I don't fix it. There we go. Okay. So, well, this will be negative 1 times cosine, so negative cosine x minus x times, well, the derivative of cosine is negative sine x, right? Plus, well, the derivative of sine is cosine x. And would you look at that? We get some cancellation, right? Because this guy and this guy can cancel. And of course, a negative times a negative, those cancel. You get, well, this isn't necessarily a positive value, but there's no negation anymore. And yeah, we do get that. So this appears to work. And whenever you check your answer on an integration by parts antiderivative to check that it's correct, well, you're always going to have this product. So you're always going to use the product rule. And that's essentially why this works. The integration by parts formula comes from the product rule, which we saw up here, right? And when you check your answer, it's the product rule that kind of causes this cancellation to pop up. So there we go. That's our first example. Okay, next example. So I'll say that this is u, Let me change colors here. This is u, and this is dv. There are because really I have three factors, and there's lots of ways to group it. I'm trying to think, how many would there be? The previous one we had 4 options. I believe here we're gonna have 8 different possible choices because I have 3 things, and for each one it's a binary yes, no. Do I include them in U, or are they included in DV, right? So I can put these 2 together in U, these 2 together in DV. I can put these together in U, these together in DV, right? I guess since 2 of the factors are the same, there's not really 8. I guess there's 6. Or is it? No, there's 7. There's 7 options, I think. 6 or 7. Anyway. So just go with what seems most obvious. Don't worry about the different options. Just go with something, and you kind of pick up after a while what's going to work and what isn't. So, um, so u equals x squared. So du equals 2x dx, right? dv equals sine of x dx. So v equals negative cosine of x. And again, if I wanted, I could say like plus 10 or plus 800 or whatever. I just don't need to. So this equals the integral, sorry, uv minus the integral of v du, okay? And I'm going to be cognizant of vertical space. So this equals, well, x squared times negative cosine x minus the integral negative cosine x times 2x dx. If I simplify this a little bit, I'll get negative x squared cosine x plus, and I'm going to move this 2 out. I don't have to, I suppose, but I'm going to choose to do that. Okay, so as before, the point of integration by parts is that the integrand you now have is easier to deal with than the one that you started with, right? X squared sine x dx is more complicated than x cosine x dx. And in fact, this one that we have now is kind of a lot like the previous one, right? So we'll deal with it the same way. So I need to do integration by parts again. Sometimes you have to do it twice. There's something called the tabular method, which we'll get to a little bit later, for handling. Well, what if you had to do it 3 or 4 times? Would you really want to write it out that much? There's a method we'll get to a little bit later. So I need to do a new substitution, and I'm not going to reuse the letters U and V. You can. Some books will do that. They'll say, okay, discard the old U and V. Don't worry about them. We're starting a new step. And we're going to reuse the same letters. I'm going to choose not to do that. I'm going to use A and B. Okay. So I'm going to say that, in fact, I think what I'll do is I'll move this over a little bit, give myself some more room on the left. I'm going to say that A equals X. Okay. It's this guy here. And dB equals cosine x dx. Okay. So that means that dA equals dx. And b equals sine of x, plus 10 if you want. So this equals negative x squared cosine x plus 2 times, well, I'm going to have, I guess I'll write it this way, a b minus the integral of b dA, okay, equals negative x squared cosine x plus 2 times, well, a times b is going to be x sine x minus the integral of b dA, so sine x dx. Okay, so this is negative x squared cosine x plus 2x sine x minus 2 times negative cosine x. And we'll put a plus c at the end. Okay. Yeah, so now I can simplify this a little bit. So I get negative x squared cosine x plus 2x sine x plus 2 cosine x, if I could write an s, plus c. So there we go. That is the antiderivative of x squared sine x dx. Or in other words, the antiderivative of x sine x. I don't need to say dx. So yeah, and if we wanted to, we could check this by finding the derivative of this entire thing and checking that the derivative is x squared sine x. I'm not going to bother in this case. You might want to do that just to confirm for yourself. Okay, so let's do an example using what's called the tabular method. So basically, I'm going to make two columns for u and for dv. And this is a little bit misleading. We're not going to have to deal with differentials directly. So, but that's the way I usually write it. So I'm going to write the thing that I would call u, and I would be the v part of dv. I'm going to put that over in those two columns. So x squared goes here, and sine x goes here. I don't need to worry about the dx. That's fine. I can, I just don't need to. So now I'm going to make new rows below these headers. And in each column, I'll go down the left one by finding the derivative. I'll go down the right one by finding the antiderivative. So 2x, 2, and 0. And I'll stop at 0. I don't need to go further because they're going to be 0 after that. So now here I'll do antiderivative. So negative cosine x, negative sine x, and then cosine x. And I'll stop here because I don't need the next one. Now I could say, oh, well, that's going to be, what is that? Sine x, negative cosine x, and so forth, right? But you're going to see why it doesn't matter in a second. What I'm going to do is, starting with the x squared, the top entry in the u column, I'm going to connect that down diagonally to the other column, but going down one row, right? And what I'm going to end up doing is multiplying those together. I'm going to end up multiplying these two and these two and these two. So in this last row, when I multiply these two, I have 0. It ends up going away, and all of them will be, right? Because I'm going to have a 0 here and a 0 here. So the next pair, they don't matter. So I don't need to write them at all. So let's just get rid of that. Yeah, so once you have 0 in this row, you don't need to make more rows after that. So there's another catch here. This first connection here, I'm going to label with a plus, then a minus, then a plus. It just alternates. Plus, minus, plus, minus, plus, minus, however many that you have. So what I'm going to do is take this pair, multiply them, and then don't change the sign. So I'm doing like plus x squared times negative cosine x. Then I'm doing negative 2x times negative sine x, which of course the double negative will cancel out. And then I'm doing plus 2 times cosine x, okay? So that gives me that this equals negative x squared cosine x plus 2x sine x plus 2 cosine x, and of course always plus c at the end. So whenever you have where the thing you would like to use for u, its derivative after a few cycles becomes 0, that's when the tabular method is going to work, and it's way less writing than just applying the formula with u and v. So whenever you have a situation like this is the way you should do it, because it's just going to be quicker, like considerably quicker sometimes. Like if I had another row, well, that wouldn't really be much harder, right? Like if I instead of x squared, I had x to the 4th or x to the 5th or x to the 6th. Yeah, there's some more rows, but that's not that hard. Whereas trying to apply the formula, it's going to be kind of a pain. There's going to be a lot of steps and a lot of writing. So this is just a quicker method for certain types of integrals. Okay, so let's do another example with the tabular method. So I'm going to rewrite this as the integral of x cubed e to the negative x power dx. I'm going to call this guy u and this guy dv. Okay, so over here I'll have u and dv. So u, x cubed, and then find the derivative, 3x squared, 6x, 6, 0. Once I hit 0, I stop there. Over here I have e to the negative x. And again, yeah, there's a dx, but I don't need it in the tabular method. Part of the benefit is you don't have to deal with differentials at all, right? You kind of avoid that. So the antiderivative will be negative e to the negative x, and I'm using substitution here essentially. Then e to the negative x, then negative e to the negative x, and then e to the negative x power. Okay, so then I will pair these up by taking an item in the left column and pairing it with the next row down in the right column. And then the connections are plus, minus, plus, minus. So for this one, I'm going to have plus x cubed times negative e to the negative x. Okay. For this one, I'm going to have minus 3x squared times e to the negative x, okay, and so forth. So this equals negative x cubed e to the negative x, right, minus 3x squared e to the negative x, minus 6x e to the negative x, minus 6e to the negative x, plus c. And if I want, I notice all of these have a minus, right? It worked out that way because half of this column has minuses already because of the antiderivative, and then the other half has a minus through the technique of the tabular method. But then also, I notice every term has e to the negative x in it. So if I want, I could factor a little bit, and I could say, well, so optionally, this is negative e to the negative x times x cubed plus 3x squared plus 6x plus 6 plus c. So in this case, it turns out that these items are just in parentheses. That's not always going to happen. The fact that I have a minus sign in the exponent is why I get this alternation of well, I get alternation of minus signs in one place and another place, and ultimately all of them get a minus sign because of that. That's not always going to happen, but sometimes it will. Okay, so here's another example where we're gonna use integration by parts. This one's gonna work out a little bit differently. I noticed that if I were to say that this is u, then the derivative is just e to the x, e to the x, e to the x, e to the x. So the tabular method is not going to work. And if I use this as u, like if I reorganize things, if I shuffle the order and put cosine x first and pair the e to the x with dx, well, then my derivative will be, well, negative sine x, negative cosine x, sine x, cosine x, negative sine x, negative cosine x, and so forth. You'll never get 0. So this one works out a little bit differently, and the only thing, well, not the only, but the way to get started is just get started. I'm going to call this u, and I'm going to call this dv. Okay, so u equals e to the x, so du equals e to the x dx. Okay, dv, this equals cosine x dx. So v equals sine of x. And again, plus c if you want, but you don't need it. So this equals uv minus the integral of v du, which is e to the x times sine of x, minus the integral of sine x times e to the x dx. And you might notice, this integrand does not really seem any easier than this one. It seems like it didn't work. Like nothing, we didn't really get anywhere. But in this case, it turns out we did. It's just not obvious yet. So we just have to do the application of integration by parts again. So I guess I'll change colors here. I kind of meant to have these in blue as well, just so they stand out. That's fine. So again, what I'm going to do is I'm going to change the order. I need to switch the order of these factors. So this equals e to the x sine x minus the integral of e to the x sine x dx. Okay. So we're going to say that this is a, and this is db. Okay. So kind of running out of room here. Well, no, we're good. Kind of glad I zoomed in now. Okay. So A equals e to the x. I guess I could have used u again, but whatever, that's fine. db equals sine x dx. So dA equals e to the x dx, and b equals negative cosine of x. Okay, so over here, that means I have e to the x sine x minus parentheses ab minus the integral of b dA. Okay, which, do they have a lot of vertical space? Yeah, I think we're good. So this equals e to the x sine x minus ab, which I won't put in just yet, plus the integral of b dA. Okay, now I'll plug that in. So e to the x sine x minus a times b. So e to the x times negative cosine x, but I'm subtracting, so it's really plus e to the x cosine x. Plus the integral of b dA. Okay, so this equals e to the x sine x plus e to the x cosine x minus the integral cosine x. Well, I can change the order e to the x cosine x dx. You might say, no, this didn't work at all. This is even worse. Look, it's the thing we started with. We've gotten nowhere, right? We're back where we started at. But actually, that's okay. Because of this minus, that means I can say that this whole thing, it's equal to the thing we started with, right? So I'm going to write it over here. Okay. Because on the right, I have this integral subtracted. I'm going to add to both sides the integral of e to the x cosine x dx. So on the left, I'll have 2 integral e to the x cosine x dx equals, and I can factor if I want, e to the x times sine of x plus cosine of x. I don't have to, but that's fine. Then I can divide by 2 on both sides. So the integral of e to the x cosine x dx equals 1/2 e to the x times sine of x plus cosine of x. So yeah, there we go. That's another way that integration by parts can work out. If you have a function that requires it, this will happen sometimes. It's hard to say when it happens. I guess when you have a trig function and exponential, then maybe. It just depends on what's present in the integrand. So now we're going to look at antiderivatives of inverse functions. There's at least 2 ways to do this that I know of. I'm going to use a technique that is done in another textbook, not the one that we're using. I just think it's more. It's not that it's easier; it's that it's more broadly applicable and it's more clear how to apply it to other inverse functions. For example, inverse trig functions. So I'm going to think about having the function y equals ln of x. Okay, and that means that e to the y equals x. Okay, so if I find the differential of this, that means that e to the y dy, because the derivative of e to the y is e to the y, equals dx. Okay, so I'm going to make this replacement. It's almost like we're doing a substitution and integration by parts. So I'm going to replace ln of x with y, and I'm going to replace dx with e to the y dy. So we're going to switch over to y as a variable instead of x as a variable. So it is a substitution as well as being, you'll see the integration by parts emerge basically right now. So that's y times e to the y dy. Oh, this is an example where we could use the tabular method if we wanted to, but we don't need to, but we could. So I can say, let's go ahead and do that. Let's use the tabular method in this case. So I can say that u And dv, well, this is y and e to the y. Okay, so the derivative of y would be 1 and then 0, right? The derivative with respect to y is our current working variable, right? Not with respect to x. So that antiderivative is e to the y, and so is that one. And then I can connect these. This one with a plus, this one with a minus, right? So this equals y e to the y minus e to the y plus c, right? So we did a change of variable, a substitution, and then integration by parts using the tabular method in this case. And I think typically you would be able to use a tabular method for an inverse function. So the problem here is that x is the variable that we're asked about. That can't be my answer. I have to switch back over, right? When you do substitution, you switch back over at the end. So now you switch back. So y, that's ln of x. E to the y, well, that's x minus x again, so plus c. So I can write this as x ln of x. I'm just changing the order. This is the way it's typically written. And there you go. That is the antiderivative for ln of x using a substitution and integration by parts. I'll point out, I was kind of going back and forth on which one to show, and I'm almost out of room here. So you can also do this. So maybe for yourself, you can look at say integral of sine inverse of x dx, right? You know what the derivative of sine inverse is, right? 1 over the square root of 1 minus x squared. What's the antiderivative? That's not so easy, right? Or any trig function. So maybe you should do a tangent as well. Tangent inverse x dx. Like, what are those? And basically, this is the approach that you use, and you should be able to use the tabular method for those as well. So now we're going to look at integration by parts for definite integrals. So I'm just going to cite the formula. I'm not going to justify it really beyond just saying, well, it's kind of like the one we already have for an antiderivative. So the integral from a to b of u dv equals the product uv evaluated at a and b minus the integral from a to b of v du. Okay, so there's just formula. We'll just use it. In order to apply it to this one, we're going to have to use a different, I don't want to say have to, we're going to use a different approach to finding the antiderivative. I'm not just going to cite the one we just got done doing. I'm going to use a slightly different method. So I'm going to say that u equals ln of x and dx is dv, okay? And for this one, I'm not going to use the tabular method. So if u equals ln x, then du equals 1 over x. Dx, sorry, dx. And if dv equals dx, well, then v equals x, right? So over here, I guess I don't need that equal sign here. Over here, well, this is going to equal u, which is ln of x, times v, which is x, evaluated at 1 and 2 minus the integral of v, which is x, times du, which is 1 over x. And I forgot the 1 and the 2, dx. Okay, so this equals, well, ln of 2 times 2 minus ln of 1 times 1. And you might remember what ln of 1 is. We'll talk about that in a second. So minus the integral from 1 to 2, well, x times 1 over x is just 1, so this is dx. Okay. So this equals, well, 2 times ln of 2, I just prefer to write in that order, minus 0, of course. Ln of 1 is 0, minus, well, the antiderivative, the integral of dx is just x, evaluated at 1 and 2. So this is 2 ln of 2 minus 2 plus 1. So I get 2 ln of 2 minus 1. And if I want, I can move this 2 into the exponent. So if I want, this is ln of 4 minus 1, if I want that. Not necessary, it's optional. Another option would be to just cite the antiderivative we've already found and just evaluate, and of course you'll get the same thing that way. Okay, so let's do an application problem. We're going to find the volume of the solid form by rotating the region under the curve y equals sine of x on the interval 0 to pi about the y-axis. So I got the function graphed here, and some superfluous part of it, but that's fine. So we want to take this curve. I'm going to try to trace it in gray. There, I just wanted to stand out a little bit more. So let's try to highlight it. So we're going to take this region, and we're going to revolve it about the y-axis, okay? So what is that going to look like? Well, if we try to do the washer method, we're going to run into a lot of problems. It's really going to become incredibly messy because this function is not one-to-one. So if I go to do the washer method, right, and I get a horizontally aligned rectangle, then the short side, of course, is dy. The long side is interesting. If we call this x, then how much is this one? It's not an invertible function, so we're going to have something like pi minus x, right? We're going to be squaring. We'll have sine inverse of y and pi minus sine inverse of y. And we'll square this and square this. It gets real bad real fast. So let's not do any of that. We're going to do the shell method instead. So we're going to do the shell method. Let's say like that, okay? So we are going to be, I will try to make a reasonably good, yeah, that looks pretty good. It's not perfect, but it's good enough. There we go. Okay. It's a little tilted, but that's fine. So we need to find out what is the volume of that cylindrical shell, right? The thickness of the wall is dx, right? The height of the wall is sine of x, right? What is the circumference of the wall, right? Circumference, well, that's going to be 2 pi x because the radius is x from the origin out to the wall, right? So that means that the volume, dv, is the product of those three things. So that means that dv equals 2 pi x times sine of x dx. So that means that v equals the integral from 0 to pi, right, of 2 pi x sine x dx. And this is an integrand that previously we could not deal with. So back in chapter 2, I guess this was 2.3, I want to say, 2.3, I think, for shells. We couldn't have handled this. There'd be no way to do this integral because we didn't have access to integration by parts at that point. But now we can. So I'm going to move the 2 pi out front. 2 pi times 0 from 0 to pi of x sine x dx. And there's two approaches to this. And maybe we should do both. I can just take, I can find the antiderivative and then just apply the fundamental theorem to evaluate. Or I can use that formula we had earlier for the integral from a to b of u dv. Either one is fine. It doesn't really matter. I'm going to go with using the formula because I think that's the least familiar, and maybe we'll do the other approach as well. So I'm going to say that u equals x and dv equals sine x dx. So u, I guess I'll put it down here. U equals x, so dx equals, sorry, du equals dx. dv equals sine x dx. I think we've done, I feel like we've done exactly this one already. I'm pretty sure we have. So then v equals negative cosine x. And again, plus 10 or plus pi, whatever you want, that it'll be fine. That'll work out, no problem. So this equals 2 pi times, well, that's going to be uv evaluated at 0 and pi minus the integral from 0 to pi of v du. Okay, so this is 2 pi times, well, that's going to be negative x cosine x evaluated at 0 and at pi minus the integral from 0 to pi of negative cosine x dx. And this integrand is a lot easier to deal with than the original. So, close parentheses. So this is 2 pi times, well, I guess that's negative pi times negative 1, right? Cosine pi is negative 1, minus, well, plus 0 times 1. Okay, minus, well, you know what? Let's make this is plus plus, right? So plus sine of x evaluated at 0 and at pi. So 2 pi times pi plus 0 plus, well, sine of pi is 0, sine of 0 is 0. So I get 2 pi times pi, or 2 pi squared. There we go. That's the volume of that. It's sort of like the bundt cake example we did previously, a little bit. The one we did originally was a parabola, but this is kind of a similar shape. So there we go. Let's take a quick look. What if we did this the other way? Just citing the formula rather than working out I'm sorry. Yeah, rather than citing the formula, what if we use the evaluation theorem a little more directly? So if I had integral 0 to pi of x sine x dx. I'm not going to work out all of it because we kind of have done it already, but basically that would be like this. We would say, okay, I'm going to find the antiderivative first. I'm not going to do the definite integral to start with. I'm just going to do the indefinite integral. Okay, so this is going to equal, and we've already done this, so that's convenient. This is going to equal uv minus integral v du. Okay, so this is going to be x, negative x cosine x, minus the integral of sine x dx. Sorry. Negative cosine x dx. So this equals negative x cosine x plus sine x plus c, right? Yeah, okay. Then we could say, all right, well, that means that the integral from 0 to pi of x sine x. So we end up doing this 3 times, I guess, in total in the video. Well, this is just going to be negative x cosine x plus sine x evaluated at 0 and pi. Right? So this will be negative pi times negative 1 plus 0 minus 0 plus 0. Oh, I forgot the 2 pi. Well, that's okay. That's fine. There we go. And we get 2 pi squared, of course. So, which one is better? I don't know. They're similar. On a test, basically, be careful. If you use this approach, you still have to show the integration by parts. You can't just say, oh, I'm just going to use the antiderivative that I remember. No. The point is to show integration by parts, and very likely in an exam, the directions would even say, make sure to show all relevant work. That you can't say, oh, I'm relying on memory, and we need you to show what's the method. How do you do it? Okay, so now we're going to find the centroid of the region bounded by y equals ln of x, y equals 0, and x equals e. So there's the natural logarithm, and then a vertical line at x equals e. And we're going to be finding the centroid of this region here. And there's no symmetry we can use. Nothing's going to be just in the middle. So we're going to have to calculate both the moment about x and the moment about y. Okay. So basically, we can just use the formulas that we developed previously. So well, this is the integral from 0 to e of ln of x dx. Okay. And I'm just going to cite, we've already worked out the antiderivative for ln of x. I'm just going to cite that antiderivative. So this equals x ln x minus x evaluated at 0 and at e. Not 0. Why am I saying 0? 1, of course. I'm seeing this. That's why I'm thinking 0. But the root is at 1. At 1 and e. Okay. So this will be e times ln of e minus e minus 1 times ln of 1 minus 1. Of course, ln of e is 1. So this is e minus e minus, well, 0 plus 1. So we get an area of 1, which I don't know about you, but to me that's a little surprising. That seems like, huh, really? 1? That's unexpected. But there we go. That's the area we get. So now we can look at the moment about the y-axis. Okay, so this is going to be the integral from 0 to 1 of, well, remember, we're always thinking, what is the torque? So the distance from the y-axis would be x, right? X times, well, what is the area? Well, the height, if we pick a representative, I mean, I said we were just going to cite formulas, but to be honest, I don't remember the formulas. I don't like memorizing formulas. I prefer to just build things out. So although I said we would just cite the formula, we are apparently not doing that. So the height is ln of x, right? And then the width is dx. So that's the area. So that's going to be ln of x dx, right? So now I have a different, why am I saying 0 to 1? It's 1 to e, sorry. So now I have a different function that requires integration by parts. But we know the antiderivative for ln of x. So I can say, oh, okay, that's fine. This will be my u, and this will be my v, dv rather. And I could even use tabular method in this case. I think that'll work. So let's try it. So u dv. And in fact, I'm going to put these over here. Well, that's fine. I can just move them afterward. So I have x, 1, 0. I have x ln of x minus x. Ah, okay. I see what's going to happen. So we would run into a problem. What's the antiderivative of x ln of x? Well, if I knew that, I wouldn't be doing this. So we should not use the tabular method. That's not going to work. So we'll use the other approach instead. So u equals x. Oh, you know what? This is a case where I don't want that order. I'm going to switch the order on this one. So this is the integral from 1 to e of ln of x times x dx. And the reason I'm doing that is that the antiderivative of x is really simple, and the derivative of ln of x is also really simple. That's going to be much easier. I don't want to say the other approach would not work, but I suspect that it wouldn't and or just become overly complicated. So this is what we really want. Okay. So, yeah, so u equals ln of x, dv equals x dx. Okay. So du equals 1 over x dx, and then v equals 1/2 x squared. Okay. So this equals ln of x times 1/2 x squared evaluated at 1 and at e minus the integral from 1 to e of 1/2 x squared times 1 over x dx. Okay? So this we'll leave as is for now. We'll work that out in the next step. So 1/2 x squared ln of x minus, I'll put the 1/2 out in front, I suppose. So this simplifies just to be x. Okay, so this equals, yeah, and I'll leave this as is for now as well. So 1/2 x squared ln of x, evaluated at 1 and at e, minus 1/2 x squared, evaluated at 1 and at e. Okay, so we're going to have e squared over 2 times ln of e, which is 1. That's from evaluating this at e, minus 0. It's from evaluating this at 1. So ln of 1 is 0. Minus 1/2 times 1/2 e squared minus 1/2. Okay, so I get e squared over 2, or in fact, I'll do this. 1/2 e squared minus 0, so I don't need it, minus 1/4 e squared plus 1/4. So I get 1/4 e squared plus 1/4. Okay, so that means if I want, I could go ahead and find x bar now if I wanted to, but we'll wait till the end. So let's go find the moment about x. Okay, so this is the integral from 1 to e, and I like to think about the not the formula, but the torque involved. So what is the distance from the center to the y-axis? Oh, we did that one already. Sorry, to the x-axis. My mistake. And then what is the area? Well, that's going to be 1/2 of the height. So it's ln of x over 2, 1/2 of the height. So ln of x over 2 times the area, which was ln of x dx. Okay. So this is 1/2, 1 from 1 to e of ln of x squared dx. Okay. So I see a couple of ways to handle this. I think we could do a substitution. Y equals ln of x may work just fine. But I think also we could try doing integration by parts with u as ln of x and dv is ln of x dx. And I'm not sure which one's going to be easier. Since this section is on integration by parts, we'll go ahead and do that. If it becomes too messy, we'll switch over to substitution. Oh, by the way, I've never worked this problem out before. You may have noticed. I like to include some problems where I don't already know exactly how things are going to go, and if I make some missteps, I will leave them in. So we'll see how this goes. This one I was pretty confident I knew what to do with it from looking at the problem, but MX I'm not certain. I don't remember having done this recently. So, yeah, we're going to do substitution. We're going to say, okay, this is 1/2 the integral from 1 to e of ln of x times ln of x dx. And this is going to be our u, and this is going to be our dv. And we will see how this goes. This may not work out the way I'm expecting it to. We'll see. So, u equals ln of x. Okay, so du equals 1 over x dx. dv equals ln of x dx. So v, and I'm not going to work out the integration by parts for ln of x. We've done this one already. So this is x ln of x minus x. Okay, so coming down here, the new row. So this is 1/2 times ln of x times x ln of x minus x, valued at 1 and at e. Okay, minus the integral from 1 to e of x ln of x minus x times 1 over x dx. And yeah, I think this is going to work out rather nicely. I mean, it's not nice. It's kind of messy, but it's going to work out. So, close parentheses. So I'm going to go ahead and leave this as is for now. We might need to spill onto the next page. We'll see how it goes. So 1/2, and in fact, no, that's fine. That's fine. I probably have room. So 1/2 times, oh, I have a mistake. I wrote ln, that's ln of x. There we go. It's probably how I should write it. Okay. So ln of x times x ln of x minus x evaluated. Oh yeah, I didn't put the bracket in. Bracket evaluate at 1 and at e minus. Now this is where things get interesting. When I distribute this 1 over x onto this term, I get 1. And here it'll cancel with this one. So I'll get ln x minus 1. Well, isn't that convenient? Okay, because this is something we know how to deal with, right? We've done this, we've done that one before. So this is 1/2. Try to write it more neatly this time. Ln of x times x ln of x minus x evaluated at 1 and at e minus x ln of x minus x minus x, right? Antiderivative of 1 is x, evaluated at 1 and at e. Okay, so there's probably some clever algebra we could do. I'm not going to bother trying to be clever. We'll just kind of brute force it. So this equals 1/2. Oh, close parentheses. 1/2 times, let's say ln of e, that's 1, times e times 1 minus e. Yeah. Minus 0. ln of 1 is 0. Minus e minus e minus e minus 0 minus 1 minus 1. I think that's right. Like I said, it's not. I started to say that this was we're gonna work out really nicely. Well, not nicely, but we're getting something. Okay, so this is, well, 0, right? Um, plus e plus 2. No, minus 2. Minus 2. Okay. Let's do it this way. Make sure that things are clear. Okay. E minus e is 0. 1 times 0 is 0. Minus 0 is 0. E minus e is 0. So we have remaining minus e, but it's being subtracted, so we have plus e. So 0 plus e, and then 0 minus 1 minus 1, which is negative 2, positive 2, negative 2. Okay? So this appears to be e over 2 minus 1. Okay? So what's x bar? Well, that's my, the moment about the y-axis, divided by the mass. So that's going to be 1/4 e squared plus 1/4. And something to think about, x goes from 1 to e, so x bar better be between 1 and e, right? And it should be a little bit to the right, so it should be like 2 point something, definitely not less than 2. Okay, so we're going to be able to get a pretty good idea if this is right or not. And the mass is 1, so yeah. How much is that? I'm starting to get nervous. This seems like it's too big. We might have a mistake somewhere. So that e squared is making me worried. Yeah, this doesn't seem... Oh, no, wait. Oh, okay. 2.097. Let's call it good enough. Hey, that's a little bit more than 2. I was worried for a minute there. But no, that's fine. So a little bit more than 2. So, right there. Roughly right there. There's roughly where it is. Okay, how about y bar? Now I'm pretty confident that this worked out, but, things could still go wrong. So mx over m. Well, that's going to be e over 2 minus 1 over 1, right? The mass is 1. So what is that? E over 2 minus 1. Oops. I get 0.359. Oh, and by the way, if you have to just do E on a calculator, you do E to the first power, right? The E button automatically forces you to do an exponent. You just do E to the 1. So 0.359. Does that seem right? Well, that is right about here. Yeah, that seems like halfway. So there we go. The center is at... I guess I'll try to draw it accurately. Oh, that's the wrong tool, wrong button. So x bar, y bar is approximately 2.0, what was it, 97, comma, 0.359. Okay, and these integrals all required integration by parts to solve. So yeah, there is that example.